Okay, well, we'll get started. I'm writing up your next homework assignment, which will, yay. You're going to be coding up a bunch of classification algorithms or functions. I think it'll be kind of fun. You know, I always think the homeworks are fun, but basically, you know, we learned the naive Bayes classifier, okay, and so you'll code that up. And then we learned the k nearest to neighbors classifier, so you'll code that up. And then today I'll introduce, maybe I'll talk a little bit more about k nearest neighbors, just, you know, maybe some, how you'd want to go about coding that. And then I'll start introducing support vector machines, okay, which is, I don't know, it's kind of fun. That's like a new thing in, that's only been around since the 90s, which I guess is 20 years ago, but it's relatively new in the field of statistics. Okay, so let's go back to we'll do k nearest neighbors. Okay. Okay, so we're talking about our k nearest neighbors algorithm.
Miles.
Yes. None of the screens are working. This is the story of my life. Okay. Okay, so anyway, you're watching this online. I did a bunch of stuff on the chalkboard. You missed out. Sorry. Okay. But right now I'm asking, you know, what do we do when we have ties? Between classes. Okay, so you know this, you know, a possible problem when you have, you know, more than two classes. Okay, so for example, you know, k is equal to 7, and you might have 3 in A, 3 in B, and 1 in C, right? These might be your 7 nearest neighbors. So how do we classify? Okay, and so we just have a few options. Number one is random assignment between the tied classes. Okay, so in this case it would be 50% A chance and 50% B. Okay. 2 would be random assignment between the two classes. Or between the tied classes. Using prior probabilities. Okay, and so in this case, you would go to your data and you would say, well, in my data, which class, you know, how many values are in class A, how many values are in class B, okay? So perhaps in your data, you know, it's like 70% A, 20% B, and 10% C, right? So maybe, so in the data, maybe you have 70% A, 20% B, and 10% C. Okay? So, you know, we've kind of narrowed it down to it's either going to be A or B. So in this case, you know, our probabilities would be 7 out of 9 for A, and then 2 out of 9 for B. Okay? And so in this case, you would probably do a R unif, and then if R unif is less than 7/9, you classify it as A, and if it's more than 7/9, you classify it as B, right? Do I need to write that down, or does that make sense? We're good. Okay, and then the last one, the last option for breaking a tie is you can just go through, you have 7, you say which of these 7 data points is the closest, right? So maybe the closest one is B, and then you'd say, okay, well, I'll just use my nearest neighbor, because there was a tie between A and B, and the data point that was the closer one was B. So you just use the one nearest neighbor to classify, okay? As long as it's one of the tied classes, right? If the nearest neighbor was C, you don't want to use that, okay? Use the nearest neighbor to classify, that is either A or B. Okay? And so basically, these are some options that you can run for breaking ties in K nearest neighbors. Okay. So yeah, we can run this to what are we? Do some classifications. Yes.
Would it also be possible just to take an even large sample? So if instead of having 7, you went up to 9 or something like that?
Yeah, I guess you can do that, and then just see, if I guess you can keep increasing your K until the tie is broken. I want to think, why don't we do that?
How about an infinite loop?
I think the problem is that if you do something like that, you're saying I'm doing a K nearest neighbors where I'm using K is equal to 7, except for a few points K is equal to 9, and some of the few points K is equal to 10 or 11 or something like that. And I think, I guess if all you care about is getting your classification, it's all just kind of a guess anyway. And so maybe that's okay. But I want to say, I don't know if I've seen that in the literature, and I'm thinking it's probably because they like to keep the K to be fixed and have a way to break the ties within the system that we've set up without having to change K. But I don't know. I mean, it seems like a reasonable thing to do as a human looking at a board, and you say, okay, well, inside this circle that I drew, I only I had a tie, so maybe I'll just make my circle a little bigger and go. I mean, that sounds reasonable, and generally, if it sounds reasonable to do as a person, it's probably reasonable to do as a computer. But there's always some implications that could happen when you change your algorithm, and I don't know if that's going to be called something else. There might be like a K nearest flexible K nearest neighbors algorithm that does something that actually sounds kind of familiar now that I say that out loud. Okay, so yeah, you can look forward to coding this up in the homework. I'm going to pause this for a second. All right, let me talk about support vector machines. And so first we're going to just talk about the maximum margin support vector machine, okay? All right, so we have something called support vector machines, and this has evolved to be quite a powerful classification algorithm. But first, we're going to just start off with a simple. We're going to start off with a simple case, and then we'll evolve into the
guess more complex ones. Okay, so you know we with a simple case. For classification, okay? And in this one, we have basically just two cases, okay? Two classes. And we will, the classes will get labeled as plus or minus, okay? Or we can say, you know, +1 or -1, okay? And so, you know, this is the way we label our classes, rather than doing zeros and ones, which is, you know, what we would use for logistic regression or, you know, other cases, okay? And here we'll start with just a linear boundary. All right, and so so I'll say blue will be our minus, our negative points, and then red will be our positive points. Okay, and so I'll have okay, and there's a question of, you know, where should we draw our boundary? Okay, so let's say this is our data. And I think there's kind of a natural, like, if I said I wanted to draw the boundary like this, technically is okay, but this doesn't feel quite right, you know? Like, is this boundary okay? And it's like, yeah, but maybe not the best. And so, you know, perhaps looking at this, we might prefer maybe something like this might be more preferred, okay? So this boundary may be more preferred. Okay, and so the idea behind, you know, why does this one feel not so good, yet this one feels a little bit better? What is there a? I mean, they both have, as far as their training data goes, they both have 100% accuracy. But what's kind of the? Or I mean, are you guys in agreement with me that that this boundary feels better than this one? Yeah, and what is it about this boundary that feels better about the other one?
You can shift back and forth. Like it maximize the spaces between the.
Yeah. So we look at how close this data point is to the boundary itself, and the distance between the data point and the boundary feels like it's really close here and really close here, whereas here they feel like it's a little bit more spaced out, okay? And that is the basic idea behind a support vector machine, okay? Is that we are going for the maximum margin, okay? Or you might think of it as the widest street, widest possible street. Okay, and so let's just say I'm going to let's just reduce my thing to something like this, okay? And we want to draw a boundary here. Okay. If I draw a line right here, it's even something like this, and we look at this distance here, the kind of the perpendicular distance from the point to the nearest point, we're going to call this our margin. Margin is equal to the perpendicular distance from a boundary to the nearest point. We'll say nearest point in nearest point on each side. Okay, and over here we would probably have to cut it something like this. All right, and then so we would look at this and we'd say, Okay, so here we have a larger margins here. Okay, and then so we'll say, you know, the most desirable boundary will be the boundary that maximizes the margin. Okay. Okay, and we can. I'm going to kind of just draw. So here's the. So imagine this is a parallel thing, and so this is the. It's supposed to look like a street, okay? And so, you know, you've got the middle of the street, and then this would be the kind of the gutters, street gutters or something, okay? So this, we can think of this as our kind of our street width. Okay, so let's talk about, you know, how can we classify a new point using this type of thing, okay? And we want to figure out, you know, where's our margin, our boundary, and all of this. Okay, so let's say, you know, this is our I'll just put this. Okay, and then. Something like this, okay? And so I'm going to have I'll have a vector W that runs perpendicular to our street here, okay? So, and W right now it's a vector that runs perpendicular. We haven't specified the magnitude yet, okay? So here I've got W is a vector that is perpendicular to the we'll say to our boundary line. Okay, so you know, we have not yet specified its length. Okay, but we know. I mean, you guys know about norms of vectors, right? So we can. What is this length? 1, right? This is you know, any vector divided by its norm is has a length of 1, right? So okay. So yeah. Okay, and we'll have a new point. Right here, okay, and so this is a new point x new. Okay, so x new is a vector representing our new point. Okay, now when we look at this, we can see, okay, it's going to be on the blue side, so it's going to get classified as blue, right? But one way we can decide is that, you know, if we can project, so without looking at the diagram, okay, without needing to look at the diagram, we can classify x new as, you know, minus or plus by projecting it onto the vector w, right? So how do you project a vector onto another vector? The dot product, right? This kind of, we remember this, right? So we project. So we can project x new onto w. Okay, so this is via dot product, and if you have a vector, then you can just, when you matrix multiply a vector, it's effectively the dot product also, right? So so we can do w transpose x new. This is projecting x onto w here, right? Okay, and if the projection crosses some threshold, okay, if this projection crosses some threshold c, then it will be classified as positive, and if it doesn't, then it will be classified as negative, okay? So if otherwise, it's negative, okay? Does that kind of make sense? So we're just saying, you know, you can imagine this as being some kind of like new coordinate system. It's not, but and this boundary here represents, you know, the value c on the projection. Yeah.
It doesn't matter if we use the original w or the unit of w, right?
Yeah, right now it doesn't. Okay. Well, we're gonna establish the size of W by doing some stuff. Okay. All right. So this is kind of the idea here, and we can just rearrange some terms. If I let B equal to negative C, then what I get is we will have W transpose X nu plus B now just has to be greater than or equal to 0. Okay. Okay, and then so if this is and if this is the case, then we're positive, and if W transpose X nu plus B is less than or we'll say is positive, or if it's less than 0, then it is negative here. Okay, that's all I've done. Okay, and so this gets us to our first system, which is our classification T nu. This is the classification of the new point can be said to be equal to the sign of W transpose X nu plus B. Okay, so that gets us to our first point. So we're just saying we're going to try to take the new point, project it onto the vector W, which is perpendicular to our boundary line, and then and if that thing itself is higher, larger than some constant B, then we will be positive or negative. Okay, and so this is what we've got here. Okay, so that's the first rule. Okay, and then so now we want to try to maximize the margin here. Okay. Oh shoot. Okay. Okay, so here I've got, this will be a negative point. We'll say here, and I've got 2 points. This will be a positive point, and this is my boundary here. Okay, so this is our boundary. This is our W vector, okay? And we want to maximize the margin. So the margin is the perpendicular distance between each of our points to the boundary, okay? And here, our boundary is obviously is going to go halfway between these 2 nearest points. And we're going to call this margin, the margin is gamma. Okay, we're going to call this gamma. So this distance is gamma, and this is gamma, and the total distance from here to here is going to be 2 gamma, right? From here to here is 2 gamma. Okay. All right. What is gamma itself? Okay. Gamma itself, or this thing, is we are basically projecting. Let me use a different color. So here, if I call this point x2 and x1, okay, then the vector that connects x1 and x2 is I have a is just the difference vector, right? Okay, so if I do x1 minus x2, that's the vector that connects the two, right? The difference between vectors is basically the vector that connects them. Okay, and so this vector, which goes from here to here, this vector is x1 minus x2. Okay, and effectively I am projecting this vector, this distance, onto a vector that is perpendicular, or that it runs parallel to w. Okay, so I'm going to project this vector onto w to find out, to get this 2 gamma vector, right? So here we can kind of see that if I project this right here onto here, right? So this vector 2 gamma, the distance 2 gamma is the projection of x2 minus, or x1 minus x2, it doesn't really matter, onto a vector parallel to w, or projecting it onto a parallel vector is projecting onto the vector itself. Okay. And so to get this magnitude, I'm going to project it onto the unit vector that is in the direction of w. Okay, so I'm going to project this onto the unit vector in the direction of w, right? So the unit vector in the direction of w is w over w, okay? And so this gives me my my next equation, which is going to be that 2 gamma is equal okay, and so that's this is I guess this is all the time we have for today. So this gets us to how we're trying to set up ourselves to maximize this margin. So we've got 2 gamma as the projection of the distance between these things onto the vector that is perpendicular to the margin here. All right, perpendicular to our boundary.